In this video, I'm going to explain what truth tables are and show you what they look like for each truth functional connective that we have. In the next video, we'll look at how we can use them in order to determine the truth value of complex propositions. Remember our syntax? It was a list of what counts as a well-formed formula in our language of propositional logic. Now here's the situation. We have basic propositions. Remember, propositions are just claims about reality. A basic proposition doesn't have other propositions as components of it. And we said that we would use capital letters in the English alphabet in order to represent these basic propositions. And in our syntax, we made sure that any basic proposition counted as a well-formed formula. Now we also said that basic propositions can be used to create new propositions. And to do so, we identified a bunch of connectives. Before we go any further, notice that in the next clause, we're using Greek letters to stand for our well-formed formulas. Now remember, these are well-formed formula variables. And if you don't remember what those are, you can go back to our video on 2.4 and I'll explain there why we're using Greek letters here instead of letters in the English alphabet. Now down here, we listed rules on how we're going to use these connectives to attach to previously existing propositions to create new ones. And we've already said that we can do this an indefinite number of times, so we can create any number of well-formed formulas that we want. But the fact that we've identified how to create new well-formed formulas using these connectives really doesn't mean that much. All that tells us is that this is what counts as a well-formed formula in our language, that we can actually use it. Now, consider our proposition alpha. Now, we're assuming the principle of bivalence, and again, if you don't remember what that is, you can go back and check the video on that. But because of that, alpha must be true or false. And because of the principle of non-contradiction, it can't be both. Now, using our syntax, we know that we can create a new proposition using alpha by just throwing that negative sign in front of it. What is the truth value of this new proposition, not alpha? Well, we want this symbol to do whatever it is that we do when we deny a claim about reality. So let's say, for example, that alpha stands for the proposition all cats are gray. Well, if that is actually the way that reality is, then that proposition is true. So what happens when we make a claim that denies that proposition? When we say, for example, it's not the case that all cats are gray, which would be represented by this not alpha here? Well, intuitively, that claim about reality would be false. And by the way, when I say intuitively, all I mean by that is I'm not proving anything here. I'm not using our rules of logic yet. All I'm doing is appealing to something that we both can see is obviously true. So intuitively, if the proposition all cats are gray is true, then the proposition it's not the case that all cats are gray is false. So here's what we're going to do. We're going to assign the truth value of false to this proposition non-alpha every time our proposition alpha is true. And what about when alpha is false? Well, it seems, again, intuitively like we'd want to define our not alpha proposition as true. And notice, we've exhausted our options here. Alpha has to be either true or false. It can't be both. So there are only two possible options for alpha. And given those two possible options, we've defined options for not alpha. So what's happened so far? We've built this truth table to reflect what happens when we deny a proposition. The syntax told us what we want to do with that connective, that negation connective. It said to just take whatever well-formed formula you've got and throw a negation sign in front of it. The truth table, however, tells us the truth value of this new well-formed formula based on the truth value of the previous well-formed formula that we used to construct it. And that is why we have a truth table for each connective. It's going to tell us what truth values our new compound proposition should get given the truth values of the propositions that we use to make it up, the propositions that compose this new compound proposition. So, new connective. Consider propositions alpha and beta. We're going to look at the connective and the conjunction connective. So let's also consider the well-formed formula that we make when we get an alpha and a beta. And we would do this by, again, using the syntax that we've already defined, but I'm not going to use that syntax anymore just because it gets tedious to keep looking at that thing. So we know that if we have alpha and if we have beta, then we can put them together in this new alpha and beta well-formed formula using our syntax. Now let's look at the different possible combinations of truth values that we can have for alpha and for beta. Well, we know one possibility is that alpha can be true. And when alpha is true, well, beta can be true. But it's also the case that when alpha is true, beta could be false. And we also know that alpha can be false. And again, when alpha is false, we know that beta could be true or beta could be false. And these are all the possible truth value combinations for these two well-formed formulas. And in an upcoming video, I'll explain to you how to figure out how many different possible combinations you can get when you add new well-formed formulas. But for right now, this is all we need to concern ourselves with 4 possible combinations. So what did we mean when we wanted to put that alpha and beta all together in one proposition? Well, we meant that you have both alpha and you also have beta. So when alpha is true and beta is true, it seems like alpha and beta should be true. So we'll assign a truth value to that t. But it seems like that's the only time when alpha and beta should be true. When beta is false, for example, it's not the case that you have both alpha and beta. So alpha and beta would be false. If alpha is false, again, it's not the case that you have both alpha and beta, so alpha and beta is false. And if you don't have either one, well then clearly alpha and beta is also false. So those are the 4 possible combinations of truth values of the propositions that can go into making up a conjunction. And given those truth values, here is the list of the truth values that the conjunction would get. Now, since the rest of my connectives are 2-place connectives, they take 2 well-formed formulas and put them together. Then all the rest of my truth tables for the connectives are going to have the same possible combinations. So I don't actually have to change the way my truth table looks right now. All I need to do is to change which connective I'm talking about, and I'm going to change which truth values that the connective gets. But notice that alpha and beta are the same, and all the possible combinations of truth values for alpha and beta are also the same. So let's consider the OR, alpha or beta. What does that OR mean? Well, we said that that OR means that at least one of these two, possibly both of them, are true. So if both of them are true, then alpha or beta is also true. If alpha is true by itself, then alpha or beta is true. If beta is true by itself, then alpha or beta is true. But if neither of them are true, then it's not the case that you have at least one of them, possibly both. So alpha or beta is false. The next one, unfortunately, is the trickiest one, and I can't really get too far into details on why it's tricky, but maybe you'll see why it is, and then just believe me that later on I'll explain it. But if alpha, then beta. That meant that if you have alpha, you have to have beta. So if you have alpha, alpha is true, and you also have beta, beta is true, then if alpha, then beta is going to be true. But now what happens if you have alpha, but you don't have beta? Well, remember, we just said that if you have alpha, you have to have beta. So then if alpha, then beta would be false. Now, the next two are the really confusing ones, but the best I can do for you, just consider what is it that makes this thing false. If alpha, then beta. If you have alpha, but you don't have beta, then this thing is going to be false. So then if I don't have alpha in the first place, then I don't really have to worry about it being false, right? So we're going to assign a truth value true to each of the cases below where I don't have alpha. Because again, whether or not I have beta doesn't matter. All I'm saying is if you have alpha, you gotta have beta. But again, that might not be totally satisfying for you, and we'll talk about it in a later video. Finally, we have the biconditional, the if and only if. Now we said that if and only if meant that if you have one, you gotta have the other and vice versa. So let's say you have alpha, you better have beta, and if you have beta, you better have alpha. So if alpha is true and beta is true, we're good. Alpha if and only if beta is also true. But what if you have alpha and you don't have beta? Obviously false. If you don't have alpha but you do have beta, obviously false. But now what if you don't have either one of them? Well, again, the whole point of this was to say if you have one, then you gotta have the other. So if you don't have one, then you can't have the other. Well, that's what we got here, right? We don't have alpha and we don't have beta. We're good. And that is the truth tables for all of our different connectives. Now, for next time, please read section 3.2, and we'll learn how to use these truth tables to determine whether a complex proposition is true or not, and also do 3.2.1 exercises.